Right, so welcome everyone to the afternoon session of the Curtin HIVE Internship Showcase. Thanks everyone for coming. I can see a few new faces this afternoon, so I'll just provide a little bit of introductions and housekeeping. These presentations are for the students who've been doing a 10-week summer internship, plus there's another supplementary presentation, which I'll mention when we get to it. Each of the students have, we've had 9 intern students this year, and they each receive a scholarship over the course of the 10 weeks. They've been working with a Curtin academic, and some of the projects are supported, the morning ones were supported by some industry partners, and actually we have an industry partner this afternoon as well, which is the Perth, or the Public Transport Authority. We're also live streaming the talks, so if you're on Twitter, or even if you're not, you can just go to that link and go to the Curtin HIVE Twitter account, and you'll get the link from there. When I get to my seat and after Wesley's emailed me the new afternoon link. What else are we? So the arrangement of the talks is, each talk is roughly 20-minute slot, which consists of 15 minutes presentation, 5 minutes of question and changeover. And so we'll have 5 talks, roughly finishing at 1:40. And then we'll have a short break while all the interns get their projects showing on the various screens. And then for the rest of the afternoon, you'll be able to try out the various systems and poke and prod and ask lots of questions. So without too much more ado, the first presentation this afternoon is by Harrison Travers. Now, unfortunately, last night he came down with food poisoning, so he's not here. That's good for him and both for us as well, probably. Fortunately, Stephanie Thomas has agreed to present the talk on Harrison's behalf. So Harrison's internship has been titled Profit versus Prevention, a Virtual Environment to Study Decisions about Preventative Activities. And Stephanie's from the School of Business and Law here at Curtin. So come up, Stephanie. And I'll give you this.
Great.
Over to you.
Okay. Thank you, Andrew. So it's really a pleasure to be here. And as was introduced, I'm not actually the intern here, so you'll get my supervisor side of the project. I took about maybe half an hour to adjust the slides a little bit so I knew what I was talking about before starting. So I'm an economist, and I'm interested in behavior, so I'm an experimental economist. So the first thing I want to do to start this presentation and motivate the project is to ask, how many of you had a New Year's resolution this year, for example, to go to the gym? Raise your hand. Okay, now keep your hand up. Truthfully, how many of you are still going to the gym or ever went to the gym this year? Okay, I see some hands go down. This is good. So I'm interested in this project. What happens in the moment? You know, we have these great ideas. We want to invest in prevention. We know it's good for us. We know in the long run we'll be better off. But in the moment, we don't do that. Things go wrong. So this project is entitled Profit versus Prevention. And what I'm interested in is creating an environment where we can start to look at these kind of decisions in the moment. So I'm being a little broad about prevention, but I'll talk more about the project. So here's the overview. I'm interested in what happens in the moment when we make these decisions. So I'm going to study a trade-off as it happens. And the reason that this is well suited for the HIVE internship is that virtual reality gives me an immersive environment where I can start to do that. So in the past, when we ask people about their health, what we're really limited to is either you are sick and you're experiencing something, or you're not sick. And I can say, so what if you did become ill? What would you do? And as we've just demonstrated, what would you do is often very different than what you actually do. So in this project, I'm trying to create an immersive experience where you have to make a decision. It's not exactly that you're sick, but it's getting close. It's getting close to illustrating this trade-off that you face. So I'll have a tangible reward in an experiment. This is pretty standard for experimental economists. We pay people, and we pay people in accordance to what they do in our environment. So if you work really hard and you make a lot of money, I'll pay you that money. And if you kind of don't pay attention and you make maybe silly decisions, you won't make much money. So there is a real tangible reward to what you're doing. But in this particular environment, I will also have an abstract reward, and it's going to be quite similar to prevention. So prevention is like, okay, you will reduce the probability that you become ill, or maybe you just increase the probability that you remain healthy, but it's not as tangible as money. And it's very similar. If I put you in a situation where you have this tangible thing, which is cash, and this abstract sort of reward. So I'm recreating this decision environment. So all you can do in my environment really is choose between a task where you earn money, and I pay you, and a task where you can do something else that influences the probability that you will be impaired. If you become impaired, your ability to earn that money goes down. So it's an abstraction of this trade-off. So what matters in the moment is what I'm really after. And for me as the supervisor, these are the questions I want to be able to answer with this environment, is like, do people really care about probabilities? Are they registering a change in probability? In the immersive environment, I can actually change how your actions affect the probability of becoming ill. Can't do that in the real world. I can change that in a very controlled manner, and I can compare treatment effects. Just be a scientist about it. So I can start to understand, like, if the probability of becoming ill changes, do you actually respond to that in the moment? Does it matter? I can change the severity of your illness, because we're going to actually impose this impairment on people. We can impose it in a controlled manner. So I can impose a really strong impairment, and everybody will have exactly the same impairment. Great new measure of control that we also don't have in reality. Because even if I could theoretically inject everyone in this room with the same virus, we'd all react completely differently. I really don't have control over what the impact of that illness would be. And in this environment, I do. I can have a little bit of impairment or a lot of impairment, and I can see how you react to that. And also, can I also introduce things like public health campaigns or reminders? Can I offer you an insurance policy? Do any of these things actually change the way that you engage with prevention? Like, in the moment, will you actually change your behavior in response to any of these treatment effects? So those are my questions. And then we had an intern come in, Harrison, and I'll say, I hope he's watching. Hi, Harrison, if you're watching. And forgive me for taking liberties with your slides, but I just adjusted a few things, hopefully, so the presentation will keep going. Okay, so here's the project. So we have this immersive environment, hopefully. You can tell me if it's immersive, because we'll set it up in the back. So it's immersive. We have this profit task. So at the top of the screen, this is the profit task. They all occur in one space. So each of these levers you see here, one's a rope, one's a lever, two levers, earns you a cash reward. And you see this on a screen right in front of you. So you can see here, day X in process. We have like 7 or 8 days you engage with. The probability that you become sick, you have this information, we're giving you all the information, how many tasks you've completed. So every time you complete one of these levers, there's a little sound that goes ding, you completed it and you earn some money, how much time you have remaining and how much you've earned so far. So, okay, this is your real reward. Then there's this impairment. So the impairment that we implemented here, this is difficult to, how do we pick an impairment, is actually your grip strength. Now, if you know anything about the health literature, grip strength is often an indicator of frailty in people. So if you lose grip strength, this is a pretty keen indicator of your health. So that was actually just a serendipitous, coincidence that it kind of matches. But it works, okay? So as you become impaired, it's harder to hold on to the lever, and you actually end up not able to hold on to it. It takes you longer to complete the task. So the amount that we impair you actually predicts exactly the amount that you should have a decrease in your earnings. Right, so we know exactly the impact now. Okay, so that's our impairment. So the thing that links this impairment and the profit task is we also have a prevention task, which is shown on the bottom panel here. And the prevention task is you just play ping pong. You don't earn any money. Maybe you really like it. Like, we had the head of the school come in and she just wanted to play ping pong. She didn't care about the profit task, but you play ping pong. And the more seconds you play ping pong, the impact of your the probability that you become ill is going down. So if you spend more time on prevention, you are less likely to have this impairment happen. At the same time, the decision remains very abstract, because you earn your money and then you do this profit. I mean, like, it's a probability, right? Until it happens, maybe it doesn't mean anything to you. So we have an experimental an economic experiment design, so it's a controlled laboratory study. That means I basically break this environment up into a number of days so that I can change treatment effects. I can vary the probability from one day to the next and compare it for each individual. I can introduce different treatments and compare to different groups of individuals, but that's all the experimental design. In every day, you start the day unimpaired, and then you face this probability that maybe this impairment happens, so you lose some grip strength, and we pay you cash. I'm an experimental economist. That's what we do. We pay you cash. And by the way, if you have questions, please stop me. Okay, so the structure of the internship was basically, I put Harrison into doing a bunch of background research, and there were two reasons for that. One was I needed him to have an idea of like what we were gonna do, so I told him, go play some VR games. Hard internship, right? And then to research some applications in VR, just broadly, go see what you can find, and many topics. So some of them were very unfamiliar. His response to me was that some of it was fun, and he was surprised at how fun research could sometimes be, which made me go, wow, as a researcher. And then I tortured him with the underlying economic model that I was going for. And then we talked a bit about health and a bit about game design. Okay, so when we were designing the impairment, what we've done is actually survey a bunch of different ways that people think about health. Like, if you think of your health, what is that? What does it mean if you're healthy? What does it mean if you're sick? So it's multidimensional, and people have looked at this. Specifically, economists have looked at health. So there are several self-reported health measures, because you think your health could be like a diagnostic, like your blood pressure, your heart rate, but health is also how you feel. Right? So there's like a general sense of well-being. So there are several general well-being indexes out there that we looked at, or compiled, if you will. All of these have in common something to do with mobility or dexterity, so your ability to navigate around your world. They all also had something to do with emotional health, and they all also had something to do with pain or discomfort. So there's a few other dimensions that are incorporated, but these are common. Pain, I'm not going to go there. I'm not going to get ethics approval to actually put you in pain, so we'll just leave that to the side for now. Emotional health, I know some of you programmers will tell me, yes, we can definitely make you feel like insanity or anxious, right? But I'm also we'll leave that one for now. We're the first study doing this, so we'll just leave that for later. So mobility, though, that comes up a lot. So in this experiment, grip strength, we're going to group that with mobility, and I guess the feedback here is that this is so common to many of these measures. Right? So we're just going to start with impairing one dimension of your health. I'm not, and like I said, I'm using the term health kind of loosely because, this isn't all of your health. It's just one kind of aspect. So then we looked at VR applications. So there were a few different applications, none that were combining both VR for experimental purposes, like controlled lab studies, and health. So the main, benefit of using VR is this immersion. So we can prompt a decision about health without actually asking you about health. So the way to think about the value of this is like, okay, so anybody who said, I'll go to the gym, maybe after this presentation you say, I said I'm going to go to the gym. You start walking to your car, right? And you say, well, I can go to the gym, or I can just go get in the car and go home, like binge watch some Netflix. Right in the moment, there's nobody that comes around and says, hey, do you want to go to the gym? There's nothing that pops up in your life. And how do you feel about your health? What does this decision mean to you? Right? You make the decision, you go on with your life. So it's a little bit more of a natural response when we can put you in some environment where there's obviously some benefit to doing this, but at the same time there's this trade-off. It's easier to kind of maybe you just keep doing the profit task instead of turning around and doing this prevention thing. So this is a first attempt, really, to study health-related decisions in this kind of an environment. So it's new. So there are two interesting studies here. So one is an effort task. So this other lab in Aachen is doing some really interesting work. And I actually had the privilege of meeting these people about 2 weeks ago. Their study looks at effort. So if there's somebody else, this is a virtual person in the background here. If there's somebody else that looks like they're doing a task, like on a production line, do you compete with it? Even it's not real. You know it's just an avatar, but do you compete with it? So that was their study. Nothing to do with health. And there are some applications, though, in health. They're just not in the same kind of economic setting. So another one is VR that we found that is used for rehabilitation. So there's a few studies that use VR for rehabilitation type things. So there's this health sort of aspect here, and there is this sort of, productivity. So we're going to bring them both together. So we'll just go back to the task. So the key components. We have this profit task with a cash payback or payment. So there's also like Harrison did some great things in this environment, and that weren't in his first presentation here. So there's actually a haptic feedback. So when you're moving these levers, there's like a vibration that handles. I encourage you to go and try out the environment, by the way. That kind of gives you a feedback about what's going on. So we tried that. There's sounds in the environment. There's a bit of like user feedback. We want this to remain immersive is the main thing. We introduced this impairment. It's a reduction in your grip strength. So we want it to remain real, so you can tell me if it feels real when you go and play the game. And we have this probability of impairment. So the way we can communicate this probability is actually a treatment effect for me as the researcher. So I can change. So I can say, I'll give you all the information about the probability that you will become ill. I could give it to you in a graph. I could use all kinds of different tools. I could give you information about your actual health. In reality, you'd have none of that, right? Maybe you just have a vague probability. If people who exercise more have a 5% lower chance of getting X cancer, something like that. So it's not specific to the individual typically, but we can look at if that makes a difference. And then we have this prevention task. The users actually influence the probability of becoming ill, and that's an important feature of this environment for me as a researcher, because in reality you don't know. You engage with, go to the gym every day, and you go to the gym every day, and for your body it means a lot, for yours it means not, like hardly anything. We don't know this. We can't really see this either in real data, but we can see it in VR. Cool. I also give people information, so their instructions, information about their health level. I can also take away this information and study the effect of that on decision making. Okay. So the scientific methodology we used here, I'm controlling key variables. That's the science of this. I can control key variables, change one variable, and look at the treatment effect of that. So it's a very simple change, and I'm looking at a response. So impairment is exactly the same for everyone, like I said before. Can't do that in real life. I impair you by 25%. What does that mean for everybody, right? In the virtual world, we can do that. I can also look at the influence of prevention on the probability of becoming ill is the same for everyone as well. I can change that functional form in the code. Perfect. Then we prompt this decision. Nobody's running around asking you to make the decision. And we observe responses. So the classic economist stuff like your earnings, right? But I'm also looking at your time use. So how much time do you spend on this earnings task? How much time do you spend on the prevention task? And then a bunch of other variables which are really nice. We can look at your movement in the virtual world. We can look at where you're looking. Maybe we need some indicator of a person's sort of ability or how well they're functioning in the virtual world. And someone who runs around a lot maybe doesn't earn as much money. So that might be an indicator of someone who's not using their time as effectively. Key hurdles in this project. This was a great slide that Harrison would have been a great person to present on this. So I guess the key hurdle would be to implement this impairment in a very realistic way. And he had lots of programming things to talk about that I don't have to talk about, I'm sorry. So we have controllers to deal with, and those controllers change depending on the interface that we're using, right? So we want to keep the movement and the interaction with the objects quite real and immersive. And we're trying to implement this grip strength thing, so that should feel real and immersive. There are lots of different impairments we could think of, but they're not all going to feel very real. If I impair your motion in the virtual world, like I was asking about the motion sickness thing earlier, you'll feel actually sick if we impair things by changing the speed of things moving in the virtual world versus the way you're moving around for real, right? So we are a bit limited with the interface. So I guess the main thing we're trying to do here is it's quite easy to impair the machines in the virtual world, right? You're pulling these levers. If we've created an experience where the levers get stuck, then we haven't given you the experience of you becoming ill. So that's this key thing that we're trying to create. So we can slow down all kinds of things in the virtual world, but does that really feel to the user like something that they're feeding back like it's them, and they can affect that? Maintaining immersion is the main idea here. So anytime things don't line up and they don't match, it just does, you forget, right? You're back in the real world now. You're not in our immersive environment anymore. And communication was a little bit of a hurdle. So at the beginning of the project, like I said, we spent about 2 weeks just doing research-based things. For me as the supervisor, I think this was really beneficial. Harrison did a lot of really good research so that he understood where I was sort of coming from when I would say this crazy economist stuff. And then we could work it out from there. We had a basis to start from. And then when he was telling me like the developer programmer stuff, I had a little basis to work from with him as well. So the communication thing. But for other projects going forward as an economist, this is, especially this type of work, I have worked on other projects with other programmers, and this communication thing is key. There's some weird stuff as an economist I need to have happen in this virtual world in order for me to draw a prediction or have any idea what to expect. And for a programmer, we might think, oh, it's a game, I'm going to make it fun. Whoa, whoa, whoa. I'm trying to pay people for doing something that should feel a little bit like work. So it shouldn't feel that fun. So everything you know about fun, like, do not that, okay? Try, right? So this is interesting, but it is the field is so new and expanding so rapidly that the next group to be able to combine this programming with the scientific methodology in this kind of setting is, I mean, papers are waiting because there's just so many things you can change and look at that we couldn't look at before. So the results, this flexible and customizable controlled laboratory environment, yes, I can change some of these parameters. I don't need to go all the way into all C# coding in Unity to do it. I mean, I don't want to mess with that, but there's a nice game manager that I can do that in. There's an immersive experience of some kind of a health impairment, but again, you tell me, is that what it feels like? And I can introduce various treatments, very nice. Click of a button, I can put things in there. One of the treatments we might consider would be like a public health campaign. If you go and look in the demo, you'll see there's a wall that is empty. It's like a concrete wall with nothing on it. It's just calling for a public health or an occupational safety poster. Next thing, a programmed data collection routine. All I really care about as the experimentalist is the data that's coming out of this experiment, right? So that's very important to me. So future work, a pilot project. So as an experimental economist, I bring actual human participants in the lab. I put them through a routine of treatment days. Everyone gets the same sort of treatment. And then I pay you for your decision. So that a pilot study is the next step here. We can look at different earnings and prevention tasks. If I have a programmer, right? We can look at different or additional impairments. So another study, I can look at self-reported health, for example. If I impose this impairment on you, and then I ask you, so how was that impairment? Do people report wildly different things, or do we get kind of the same result? Economic studies of insurance, medications, workplace, you name it. We can do all kinds of stuff in this environment. So conclusions, this was a paving the way experiment, so it was new. This is a new sort of environment to set controlled laboratory studies, many possibilities for experiments, and the pilot environment was intended to be for a grant proposal for the NHMRC to look at behavior. Okay, so there's some acknowledgements. Thanks me. Okay, great. Thanks Harrison, and thanks to the HIVE internship program. Yeah. And here we go, we tried the demo. So like I said, I wasn't lying. We actually brought the head of the school in to try our environment, and she had a great time. So you should try it too. Thank you. Yeah.
Any questions?
Yeah. So the payments are set, well, we can only set an average, so we don't know what everyone will actually do. We'd like to set this slightly above minimum wage for an hour. It doesn't take an hour.
Any other questions?
Yes.
Jack?
Okay, so you said you can alleviate alleviating impairments by hitting ping pong, right?
You can reduce the probability that the impairment occurs.
Okay.
It could still happen because it's a probability.
So does the experiment account for the possibility that someone just might not be very good at ping pong?
Doesn't matter how good you are because it's only based on the amount of time that you spend actually playing ping pong.
Okay.
So I've got a question. When the person starts out, are they told the regime or sort of like the algorithm, or they expected to work that out?
Okay, so well, there's a few ways we can set this up. So in the demo, we haven't done this, but in a typical experiment, you'd come in, you'd have one day you're fully healthy that walks you through, and there's like a tutorial and a bunch of instructions, and then one day when you're completely sick, so you know what that's about, and then you'll have more instructions that say, okay, this is what's going to happen. So there's this probability you can become ill. If you spend all of your time on prevention, you won't become ill. Basically, your probability will go to 0 or something like this. So we, in an economic experiment, are really careful to tell participants the information that we want them to know very carefully and explicitly, and we don't use, like, we wouldn't say something different. Like, we wouldn't say, oh, it's like this, you know, you can do this prevention task and maybe it will help you. It's actually what we said.
So you've got a script.
Yes.
Every person gets the same thing.
Yes, you'll see the instructions in the virtual world too.
Very good.
I can't control that you actually read them, though, unfortunately.
Ahmad?
This is a great point. I mean, we can have a tutorial. Maybe people just click through the tutorial, right? But this is a valid point. So as a classical experimental economist, if you don't like those written instructions in the virtual world, oh my gosh, you have no idea what's coming to you. Screens and screens and screens of instructions, and then pick a number and push a button, right? So those instructions are quite pared down. But as for making it more interactive, it's a very good point. Like, how do we best make sure someone's in and everybody knows the same information for sure? And everyone knows that everyone else knows the same information. So like a tutorial kind of environment to walk you through and you can't progress. Sometimes we do that. This was 10 weeks.
All right, thank you so much. Questions later, we're running over time. Stay in line, Artur. Thanks, Stephanie. Our next presentation is being presented by Daniel Adams on behalf of quite a large group of students. So this was actually a final year project in the School of Electrical Engineering, Computing and Mathematical Sciences. So the other students in this project, and it's a team of 7, so this has been substantial work over 2 semesters. So the other students are Stephen Tri-Tai Pham, who's in the back row, Kale Watts, Subhash Ramakrishnan, Emily Ackland, Ham Tran Lai, and I should have mentioned Kale's here as well. Joshua Hollick and myself have been the primary supervisor, and Hannes Herman, who's in the audience as well, has been the overall project supervisor, project lead across all of the projects in this final year scheme. So this is the development of a camera-based projection mapping system for non-flat surfaces, and what we mean is the cylinder, okay?
Thank you. While most conventional projection surfaces are flat, there are many situations where the surfaces are uniquely shaped, such as the HIVE display, the cylinder display here at the HIVE. My name is Daniel Adams, and I'll be discussing the development of a camera-based projection mapping system for non-flat surfaces. The project has been undertaken by 6 students, including myself, Stephen Pham, Kale Watts, Subhash Ramakrishnan, Emily Auckland, and Ham Tran Lee, supervised by Joshua Hollick, Andrew Woods, and Hannes Herman. The HIVE cylinder display consists of a 180-degree half cylinder, which is 8 meters wide and 3 meters tall. 3 projectors illuminate the display surface, which is stereoscopic capable using frame sequential 3D and LC shutter glasses. The complication with the current software solution the Curtin HIVE uses to calibrate their cylindrical display is that it assumes the screen is a perfect cylinder. However, this is not the case. Due to the material properties of the display, the screen tends to deform over time. This results in a substantial amount of bowing in the center not being accounted for, which translates to noticeable amount of distortion in horizontal and vertical lines expected to be straight. This project aims to provide a robust implementation where this deformation is taken into consideration, resulting in a more accurate calibration of the display. It also intends to produce several quality of life improvements, such as allowing for the user to move the viewing position in software to a new predefined location, being able to save and revert to different calibrations and configurations, to provide meaningful error logs for debugging, and the extensibility to work with other possible display configurations. The software works by sending a series of calibration test patterns to the projectors, which are photographed by a camera, processed to calculate a projection map, output as a set of warp blend meshes, which will result in a continuous screen surface that appears to have correct geometry to an observer at a predefined location. So the project has been undertaken in several modular components. First, the camera-to-computer interface should be responsible for interacting with the camera, capturing and downloading images. This should present a consistent interface that is suitable for the use with a DSLR camera, such as the Canon EOS 1200D. The image generator module must generate and display a test pattern on the screen for camera capture. Next, the image processor module should be able to take an image from the camera and detect the relevant features that are required for screen distortion correction. These features would likely be a combination of the natural features such as the edge of the screen and the projected features such as the test pattern control points, which I'll show you in a moment. The geometry computation engine should use these features in the image to calculate the final display geometry. Finally, the warp blend output module should be capable of writing an output files for the projection design barcode WB2560 warp blend units. So the camera to computer interface module is responsible for remotely controlling the AV, TV, ISO, focus in and out settings of the Canon EOS 1200D camera, allowing the user to view a live feed of what the camera sees within a GUI window. This is done by utilizing the Canon Digital SLR Camera Software Developers Kit. It must also provide a framework of automating the test image capture sequence whereby a camera takes a photo without intervention from the user and saves it to file. So the image generator module is responsible for generating a sequence of test patterns to be sent through each projector and displayed on the screen. The module should be able to black out all other projectors not in use when the test pattern is only required to be displayed through a single device. When the user clicks Start calibration in the GUI, the image generator module loads the blank screen test pattern into memory and displays it on all devices. Control is then given to the camera to computer interface to capture an image of the test pattern on the screen. Once the image processor module verifies that the whole screen is in full view of the camera, the image generator module must begin the sequence of projecting the rest of the test patterns to each individual projector, again giving control to the camera to computer interface to capture and serve those images. You can see the different test patterns. The image processor module is responsible for detecting if an invalid image has been taken, i.e., as I just said, if the full screen is not in frame of the camera, and then deriving the intrinsic and extrinsic properties of the camera via pose estimation, then performing appropriate feature extraction on the captured test images. With this information, it must then scan the detected points from an unordered list of coordinates into an organized data structure, map these points to their corresponding actual projected coordinates, and finally iteratively interpolate between each detected point. When a captured image is first loaded into memory by the image processor module, it undergoes an initial stage of pre-processing to reduce noise before any feature detection can be performed. Next, the edges of the whole screen is detected and a mask is generated to constrain the feature extraction space. The corner points of the full screen mask is detected, as you can see the red dots, and saved in a data structure to be used for pose estimation later. This mask is applied to the image again, and a new mask of an individual projector is generated, constraining the feature extraction space even further. The module then extracts the center projection from the 2x2 box test capture and a series of control points on the 48x30 box test capture. Then a middle out algorithm was created to scan these features originally detected and stored as an unordered list of coordinates into an organized data structure of control points, from the only concrete point being the center of projection, as you saw from the 2x2 test pattern. The algorithm works by searching for the nearest neighbor at an expected distance away from the most recently mapped concrete control point, and then appending this new point to a table data structure of control points. This process continues in the above-mentioned middle-out fashion until all unordered coordinates have been mapped to a corresponding concrete control point. Once this table data structure of concrete control points has been created, we again use the center of projection and the expected distance between points, originally 40 pixels, to calculate their corresponding flat ideal projected coordinates, as you can see. Finally, to increase the density of control points, we subdivide the table and perform point interpolation, effectively doubling the height and width of the table. This process is repeated until the ideal distance between the points is reduced from the original 40 pixels, as seen on the original test pattern, down to 2.5 pixels. This is just after one interpolation. So instead of 40, it's down to 20 pixels distance. The geometry computation module is accountable for using the control points and extracted features from the image processor module to calculate the correct display geometry and to generate a warp mesh for the screen. This is achieved through the use of projective geometry and by employing the concept of the pinhole camera model. It must also enable the user to manually adjust the viewing position that the display is calibrated around by an amount predefined in a GUI configuration menu. Upon successful completion of the image processing, the system begins the process of geometry computation and screen calibration. The geometry computation module works by projecting a point we refer to as the ideal virtual coordinate through an imaginary plane, and then which is then wrapped around the physical screen represented by the laser scan. This is achieved through the use of ray casting. In order to locate where the light ray intersects with the laser scan, all rays must be projected from a consistent origin, this being the center of the laser scan. The spherical coordinate system was used to determine a necessary angle at an ideal virtual coordinate, finally generating the 3D object coordinate, representing its nearest neighbor on the laser scan. Using the intrinsic and extrinsic properties of the camera, derived from the pose estimation calculations in the image processor module, the corner points of the 3D laser scan are aligned with the corresponding corner points of the full screen test image. When we then perform a 3D to 2D projection on the newly generated object coordinate to find the relative 2D image coordinates as detected by the image processor module. Once located, we retrieve the 2D image coordinates corresponding projected coordinates, thus completing the process of mapping a detected feature to its own flat ideal space. The final geometry data is structured as a warp mesh consisting of ideal coordinates and actual projected coordinates. It is then written to an intermediary output file along with the calculated projector overlap amounts, which will be read in by the warpLen output module. The core purpose of the warpLen output module is to interface with the projection design barcode WB2560 warpLen hardware in order to send and apply the generated warp mesh to the projector output. It must also apply illumination and transparency blend to the overlapping regions of the projectors and provide a framework that enables the user to save a calibration, avoid overriding the current calibration, and be able to revert to a previously used calibration. Finally, here we have the results of our generated warp mesh, soon to be applied to the actual cylinder display. Keep in mind, we're trying to visualize a 3D mesh of a curved surface on a flat screen, but note the curve on the left side of the screen, and also on the right side, which is accounting for the bowing in the center of the screen. You can also notice the curve on the bottom of the actual image, representing the true curvature of the cylinder. This presentation has provided an overview of a capstone computing project undergone by 6 students for the Curtin HIVE over the course of 2018. The project has been a great learning experience for all students and the HIVE staff. The project is in its final stages of becoming a functional prototype, with each module integrated with the system and the results of the final output calibration currently being refined. Future plans for the software will be centered around increasing the accuracy of the calibration, reducing the time it takes to complete a calibration, and general usability improvements on the side of the GUI. Thank you for listening, and I'll be happy to answer any questions.
Any questions? Sue?
This isn't my area, so I hope that I understand what you were talking about. But in terms of the cameras that you have there, would you have to then create a new system, a new set of programs for different cameras at different locations?
So we'll repeat the question. So Sue's asking whether if we were to apply this system to another display and another camera, would we have to make any changes?
Well, the final output mesh, that's written to an intermediary file, which basically what we hope to achieve is basically if you want a different set of hardware, rather than putting it through the barcode design WAP-LAN units, if you just want to send it straight through a projector, we could just write a plugin that will basically read that intermediate output file and write it to the correct input for that device.
So what sort of things would you change if it was for another display? A laser scan is one.
Yeah, the laser scan.
The camera model for the camera.
Well, I think that was dependent on the actual laser scan as well, because I think the point cloud of the laser scan was saved in the spherical coordinate system as well. You'd also need to be able to sort of know the overlapping areas of each projector, so the way that we sort of scan across the screen to determine the overlapping areas of the projector, that would have to be made a little more robust. Otherwise, like, it should work.
Thanks, great work.
Any other questions from the audience? No? Okay. So thank you, Daniel, and we'll start moving across to the next presentation. Thank you.
Thank you.
All right, after a quick battery change, our next speaker is Benjamin Cheng. He's been doing a project under the supervision of Mihei Wan from the School of Education. Mihei's right here. I think Benjamin's been having too much fun shooting arrows in VR. So, over to you.
Hi, good afternoon everyone. My name is Benjamin and I'm a third year computing student in Curtin. So over the past 12 weeks, I've been working on this project of visualizing Newtonian physics through an archery simulation over the summer. I believe that when we are interested in a topic, we are more motivated to learn more about it. When we think about simple projectile motion, we only think maybe, a higher gravity so the arrow falls faster. But that's not all there is to it. We aim to use this VR technology to create an immersive and interactive experience, to motivate users to learn, understand, and apply certain concepts in a fun environment. This brings us to the three main goals of this project, which is to be immersive, educational, and fun. To achieve this goal, we decided to use an existing asset from Steam VR's Longbow game. This asset provided us the teleporting functionality and the realistic bow and arrow mechanics and animation. However, this meant that I had to understand someone else's code. And yeah, that marks the beginning of my learning journey. So at the start of this project, I was very fortunate to be provided with a very powerful laptop, a bunch of Udemy videos to teach me Unity, and a nice comfy office to work in, thanks to my supervisor, Mihei. This was a very strong motivation to kick off the project, and I blazed through the tutorials learning about Unity, projectile physics, and how the Steam VR Longbow code worked together with the HTC Vive. Taking small steps at first, I made a 3D version, as you can see here, to learn, develop, and test new features much quicker before converting it to a VR version. I also attempted to implement networking to allow multiplayer functionality. Towards the later stages of this project, the emphasis shifted more away from developing new features to more of improving the user experience. So, This included developing and designing levels using assets such as ProBuilder, Unity's terrain, and other imported assets. By developing levels further and planning obstacles carefully, we can encourage users to think and apply physics concepts in order to overcome these challenges. The level design also helps with depth perception. And ambient sounds and music were added to add a more realistic and immersive feel to the user, such as birds chirping and so on. Lighting was used to add mood and depth to the level, as you can see here in this cave, and features such as level transitioning and data collection were implemented as well. Well, remember how I said I attempted networking? Well, that brings me to the greatest challenge encountered in this project. So networking was a major challenge and was unfortunately unable to be implemented in the timeframe provided. Networking with Unity's UNet system on existing SteamVR's code was very complicated, as the SteamVR's code was not really made for networking at all. A complete understanding of their code base would have been required to make them network compatible. Furthermore, networking involves having 2 headsets and 2 computers, so as a single developer by myself, it is especially difficult and time-consuming to develop and test new features. In addition, it was very hard to find resources about how to use UNet as it was being deprecated. Thus, we had to sacrifice networking to develop the features within the time frame. Next, depth perception was also another major consideration during development. I'm very grateful to have my fellow HIVE interns test out my program, during which they highlighted that it was actually quite difficult to gauge how far the target is. So I had to find some solutions for this, which included these things called motion parallax and occultation. By using terrain and props, we place them in front of each other to get a better sense of depth. Also, we have this Joseph figure here, which in the game is about the same height as a normal human being. And we use this so that you can see how far away it is. If it's smaller, you can know that, oh, the target is further away. So as you can see here, these illustrate the issue of depth perception. While there's a distance to target displayed up there, it says 27, but it looks very near to you. And whereas when you look at the side view, you realize, oh, it's actually really far. So that's what the main problem we had. Next, this screenshot shows how the solutions were used to improve depth perception. As you can see, this is the before and this is the after. And in here, you have little Joseph standing here, who is very brave, standing next to the target for your convenience. So that's all for my story. So now, let's move on to the key features implemented to allow users to explore Newtonian physics in an immersive, educational, and fun way. Firstly, we needed to allow users to adjust factors that affect the projectile motion. Several factors are provided, such as gravity, aero mass, and aero drag, which is air resistance, and wind. Normally, you'd have to fly to the moon to experience a new gravity. However, in this project, you get to have the absolute power to modify gravity with your bare hands right here. So, we can play the video. Yep. So as you can see, the user, me, shoots an arrow at normal gravity. Then I can change the gravity with my hands to gravity 0. Yep. And fire another one. And you can experience the effects of the change you make immediately through these visualizations and arrow trajectories firsthand. Okay, next. So yep, these are some of the trails for gravity. To show these trajectories, a trail was implemented. This trail can be toggled on or off and rotates through a color palette to allow users to match the trail to the respective data on the UI history board. So as you can see here, the first trail is a normal gravity one, giving a nice gentle arc. And the second one is the blue one, which is 0 gravity, so it's a straight line. And number 3 is the purple one, which is an arrow of high drag. Means that there's a very high air resistance, so it arcs very soon and slows down very fast, almost like how you have badminton. Yeah, so it's educational. And the factors are not only shown in numbers, but also through visual effects and sounds. For example, this meteor fall effect is scaled according to arrow drag. On the left, you can see that this is a low arrow drag, and the arrow pierces through the air very fast, and there's a wide vertical spread of the effects. On the right, when you have a higher arrow drag, you can see the arrow is struggling to pierce through the air, and there's a wider effect at the bottom. You'll be able to experience more of these effects in the demo later as well. In addition, scores and time taken for each level are recorded in a text file on each run-through of the game. Here, we can see that the user took a whole 2 minutes to finish level 8 and could not land a single shot as he got a score of 0. So from these data, we can use it to identify problems with certain levels and modify them accordingly. By observing the trend of scores in different run-throughs, we can see if users are improving or it's the same. We can confirm if learning objectives are met successfully. Hence, these key features help to build the foundation of this project to allow the goals to be met. So, what's next? Well, due to time constraints and the fact that I'm not particularly artistic, there are still lots more animations, sounds, and decorations that can be added on to create appealing levels for greater immersion. As for the scientific side, more user testing can be done. This will allow developers to modify levels in order to target specific learning objectives and to confirm if these educational objectives are actually met. Networking, to allow multiplayer functionality, will allow users to have a collaborative learning experience in future. Other methods of networking, such as using Photon or the new Unity's networking system, could be explored. While this is only an archery simulation, the underlying logic is basically projectile motion. Hence, this project can be actually expanded upon to include all kinds of projectiles. You could have different ways of launching them, new factors, new obstacles, new breathtaking scenery. There's so much more that can be done for greater immersion and fun. As a gamer, there are many cool features that I would have wanted to implement, such as fancy explosions and animations, but I'm glad that my supervisor, Mihei, kept me on track on developing this project as an educational game. Wesley encouraged me to focus more on visuals rather than numbers, as that is the main advantage of having VR after all. And Michael helped teach us best practices for developing in Unity, which helps streamline the project and keep it neat and organized. For future development, these considerations would be important points to keep in mind as well. In conclusion, this project allows users to reinforce and apply their knowledge to solve challenges in a fun and interactive game environment. Through this simulation, I hope that users would find physics even more interesting and be encouraged to pursue further learning in the process. I would also like to thank the following people for all the support given throughout this project. Thank you.
Thank you, Benjamin.
Yeah.
Any questions from the audience?
Oh, wow.
I'll explain. There's an important background to that comment in a few seconds. Anyone with some questions for Benjamin?
No, I'm not joking.
Yeah.
Sure, it was great.
I'll just play some videos while we're waiting for questions. Yeah?
Ahmad in the back.
How difficult was it to transition from regular to VR?
Oh, you mean from 3D to VR?
If you could repeat the question.
So,
Repeat the question.
how difficult it is to change from 3D to a VR environment. For that, it was actually surprisingly easier than I thought. It was just because Steam VR has an asset that allows you to convert it to a VR version quite easily. You just click their asset, drag it in, and you got a player that can use VR. So actually, it's quite fast. You just have to change a few settings, link up some variables, and it's done. Can be done within a few minutes once you get how to do it. Yeah.
Once you've done all the other hard work.
Yeah. Yeah.
And how many other VR experiences have you developed, Benjamin?
Just this one. Yeah.
None.
Yeah.
Any other questions from the audience? When can you experience it?
Soon.
The demonstrations afterwards?
Yeah. Okay.
So your demonstration will be on which screen?
Over there?
On this one.
Yeah, on the TV screen.
Yeah.
Thanks, a good question. So I'm wondering what type of pre-built templates did you use? And for the UI factors right there.
Yep.
So you custom built that, I imagine, for the project. Yeah. So for other projects where you might need something like a checklist or something like that, what's the best way to convert that into this type of setting?
For VR, the one consideration that I was taking in was that you don't want to keep it too much of like, you know how in 3D you have your mouse, you can click on things, check boxes, you can sliders. But in VR, you actually have like hands to do things in 3D. So I tried to keep it away from like you point at something and dragging it. So for checkboxes, you could probably keep it as a clickable button. So like maybe put your hand in something, click, and then it'll just like change. For sliders, we had this handle that we hold and drag around. Yeah, so we can convert many of the normal UI features, user interface features, into a nice VR-friendly version. Yeah.
Thanks. And then how would you capture those responses and then actually view them? So if you have,
To download the data.
Yeah.
Sorry?
To download the data, how could you download the responses?
So to gather data in this project, you mean? So like in terms of every button press or arrow or things that you slide around, they can call a function behind the scenes, and that can be written to a text file, which is like how I did my data collection on all the scores and levels. Everything you do in there, it can write to a file. And as long as you can do that, you can log everything with timestamps and so on. Yeah.
Thank you.
Okay. Question from Ahmad in the back.
Did you use an asset for the recording, or was there what was intended to write to a file? Is there an asset you downloaded and used for the recording of the data?
No. No. For in terms of recording the data, we do not have a specific asset for it. We just need to write to the file using normal file I/O, input/output. So which we have over here. Yeah. Oh my goodness. Is it right? Yes. So over here, for making this kind of thing, we'll have all the normal factors like variables encode the data, which we want to put it in a nice format like this. So in terms of code, we just have a concatenation of all the data with little headings, and we just put tabs between them so they give a nice spread like that. And that's how we collect the data on this project. Yep.
Okay. Thank you for all those questions, and thank you, Benjamin.
Yep. How do you take it out?
Don't worry. Okay.
This one. Let's see.
I'll take it. Is yours already on here? All right, let's launch it. So our next presentation is by Darp Nagarsheth, and Darp's academic supervisor is Marina Ciccarelli from Health Sciences. This project has also been supported by the Perth Transit Authority, Public Transport Authority, otherwise known as Transperth, and David and Louise are here from there. And this is another project where they've been having far too much fun collecting lots of video. And my comment about Rent-A-Crowd is that when you see the videos that have been collected, there's a big audience that was participating. And so over to you, Darp.
Thank you.
Good afternoon, everyone. Thank you for attending my presentation. Today we'll be discussing the project, a mobile educational resource for the safe and efficient use of public transportation in Perth, or as we also call it, the Get On Board VR. My supervisors, the main supervisors, were Associate Professor Marina Ciccarelli, alongside David McMahon and Louis Madden from the PTA. So what is this project about? This project was proposed to Curtin HIVE by Transport. It is a collaboration between Transport and Curtin HIVE to create accessible software that is easy to use and that enables safe and efficient use of the public transportation system. So you might be asking, why do you want to do that? Well, every year there is a huge number of users using the public transport system for the first time in their life. Out of these users, a majority will be primary kids, primary school kids who will be transitioning to high school. Alongside there will be kids who have disabilities that require assistance to transport and have their freedom. Alongside there, all the adults who have lost their ability to drive and require transportation services to move around. So what is the vision that Transport had using in this project, what they wanted to achieve? Transport wanted to achieve a mobile, educational, interactive, immersive experience, which is able to deliver the content, which is able to scale well, and also able to complement their live education that they're performing right now. You might be wondering, well, they're performing the live education right now. Why not keep doing that? Well, currently, there are some problems with that situation, that method of delivery. Currently, the information is delivered, as I discussed before, to the majority of group, which is primary school kids, in a focus group in primary schools, where Dave or either Louis go in person and deliver the presentation using demonstration and props. They also have some videos available online, which helps them deliver the information, but it is not as immersive or as interactive as this project aims to be. And there are more problems with this content delivery. As you can see, the approach is labor intensive. David or Louis, someone has to be there to perform this. There is no other way around that. It is not as engaging to children, as you can see in the picture. Not everyone is engaged in the presentation, as not everyone feels that they are being referred to. The presentation is a lecture type presentation. It is not self-paced. If you're listening to someone talk and you miss a couple words, you unfortunately do not have access to a universal remote, which you can press rewind on and listen to them again. So it is not self-paced. It has a very limited reach. As I said before, the Get On Board department is a small department of PTA. They're not able to attend to all the requests that all the primary schools or all the institutes make to make use and enable this use of transportation systems, as there is a small crowd. Also, it is immobile and impersonal. Let's say you're an international student coming into Perth for the first time. You do not have access to this information as you're not in the country. Alongside that, this information is not personal. You don't feel personalized, as it is a lecture type delivery. So what did we do to fix that? What did we do to achieve this vision of Transport? Well, we decided to make our program in Unity. Now, you might be asking, why Unity? At the beginning, I had two options. I had either use Panator, a software, or Unity as a software. I decided to go with Unity. The reason for that being, for the first and foremost, the in-house expertise available of Michael and Wesley, which is extremely useful for me and my project, as I have not used Unity before. So having someone in person available to ask questions and get feedback from immediately was crucial for my success in this project. Unity is extremely extensible. If you make a program in Unity on desktop, using a couple of clicks, you'll be able to deploy it as an app for tablets, on a smartwatch, on a VR display, on a VR head-mounted display, or even the smart TV that you might have at home, or even the dozen options that Unity supports. So it is extremely extensible. Also, the availability of online resources and training. As I said before, I have not used Unity ever in my life. So it is very helpful when Unity provides over 300 self-paced tutorials for you to learn and master Unity on your own. Last but not least, powerful. Unity is powerful. It is able to support all of the needs that I had for my project, being able to play 2D flat videos, play 360 2D flat videos, 2D videos 360, and also being able to play them together. My other option, which was Panator, was not able to achieve that, was not able to play 360 videos, so that's why I had to discard that as well. And another big factor with Unity is the asset store. You can use the asset store where you can find components which are free, and you can easily import into your project and make your project more powerful and more able to achieve the end goal. So now I have the software, but what I'm going to put in the software? Well, the software content was given to me by Transport. The whole storyboard, the storyboarding content was given to me by Transport. The story recording content, you'll be able to experience what is the story later in the demonstration area. But the main gist of it was that you need to capture the videos from a first-person perspective point of view. Alongside that, it is suited and focused to have our major audience, which is the pre-adolescents, and have them in our minds, who is going to be using the public transport system for the first time. Now, I have the story, I have the software. Now, I'm not going to get robots to do all the story because that's just robotic and not as fun. So I needed some actors to do that. And that's where all the audience comes in. So as you can see, all the audience is in-house, as some of you might know. So on a decided day, with the help of David and Marina, we all came together with a bus and a driver, and we shot all the content. As you can see, me holding the camera, I shot all the content and edited, and before I could put them in the project. Now, there is a specific reason why this crowd is chosen as to be our talent. As you can notice, this crowd ranges in ethnicity, in age, and in gender. The reason for that is when a new user is going to use this application, we want all the users to be as familiar and relatable to this app as possible. So we just decided to go with a wide range of audience, and our main actors being the pre-adolescent kids, who the kids can relate to as well. Now, I have the software, I have the videos. Now, how am I putting it together? I'm using a three-step process to put all of that together. At the first of all, I'm showing the user either a 2D video or a 360 video, immersing them in the environment, giving them instructions that they need to do, and telling them what they will be required to do in the future. Then I'm showing them an interaction where they are required to perform an interaction. And only through this way they will be able to go forward. And then in the last, when they perform the correct interaction, they are given a positive reinforcement through a confirmation video. There are two types of interactions. There is identification, where there will be a video playing, where you are required to identify one spot in the video, and also validation, where there will be multiple choices available for you to pick from, and when you pick the correct point, you'll be able to go forward. Now, this approach is a slight gamification of the content delivery, as some of you might have noticed. The reason for doing that is that it helps increase immersion, it helps increase focus, and it keeps our major target audience, and everyone, in fact, enjoy the experience while they're getting the information that they need, which is the main goal of the project. So how was I able to achieve immersiveness in my project? Well, I used a 2D 360-degree static videos to simulate the environment and immerse the user. Now you might be wondering, why is it a static video? Why not a moving video? I decided to go with a static video, as moving video usually, they require a lot of processing power, they cause motion sickness, they cause lag, and they usually are associated with nausea. So I wanted to eliminate all of that, have this be accessible also for users who are more sensitive, or probably who have certain disabilities around this factor. So this helped me achieve that. Alongside that, immersiveness was achieved by using a first-person perspective and a first-person language throughout the content delivery and throughout all the videos. Now, that's enough of me talking. Let me show you how the content software actually looks. Not really. Okay, there you go. So there we go. That's the beginning where that's Unity. That's the splash screen, the start screen. Here I'm showing the user a 360 video where they are able to move around, while at the same time I'm showing them a 2D video, which is giving them the instruction that they need to perform the task coming up. They'll be able to do both of them simultaneously, move around. Sorry, David, I had to skip you. And once the video has finished, as you notice, then you are able to interact with the scene. Here you're required to pick a scene where you think it is safe for you to stand. So you can see that is not a correct place to stand, where you're waiting for a bus. Neither is that. you'll be able to find out why, or you probably know why. I have also incorporated animations just to keep my user group in mind. Also, everyone likes animation. And these animations are randomized, so whenever you click them, there is a new animation, which everyone likes to do and find out what's going to happen again and next time. So when you click on the correct spot, you'll get a confirmation video, as I discussed before. And you'll still be able to look around. And you can see there is no other way to go out of this situation, out of the scene, as we want you to have the information be delivered to you, and then you can have the next button pop up. Going back to the presentation. What time am I at? Just a sec. How am I able to extend it?
Just go ahead, unless you need the notes.
Would like to have the notes?
Okay. So now just going to shift to 5. Oops, shift to 5. There you go.
Sorry for that. So as you saw, the software is very powerful. So what is the impact that it can have? You can say, it is a software, it is designed for scale. You can easily scale it, send it to other schools where the Get On Board team will not be able to reach. It also complements live education that David and Louisa perform. Using the software alongside the live education helps the end user feel more personalized as they're getting the information firsthand, while having an expert with them helps them if they have any questions and answer those questions. This approach also helps people and children with disabilities, mild intellectual disabilities, or who are on the autism spectrum. It helps them get familiar with the transport service while feeling less anxious and feeling more familiar while they end up being there in real life. So what is the future work that can be done on the project? All the 2D flat videos that you saw can all be recaptured to a 180-degree equirectangular video to increase immersion. Alongside that, all the videos can also be recaptured using a 3D camera to allow an in-person immersive experience using a VR headset. We are also planning to deploy this software as an app, so it has increased usability and accessibility for a wider range of audience who doesn't have access to, let's say, a desktop. And this is a proof of concept of what can be happened, what can be achieved. This same methodology can also be used and expanded to have the train or ferry or even the plane experiences for new users using the services. Lastly, I would like to acknowledge all the supports that I have received throughout this project, all the supervisors and co-supervisors, Marina Ciccarelli, Dave McMahon, and Louis Madden from PTA, Dr. Andrew Woods and Dr. Susanna Soon from HIVE for their support, the technical assistant without which this project will not happen, Michael Weber and Sylvester Lema, the amazing talent, and also, last but not least, Swan Transport for providing us with Dan the driver and a bus without any charge for the day so we can shoot this content. So that's it for today. Any questions that I can answer?
Questions?
Hey.
Cool, thanks for that. So I was particularly interested in, I guess, the app-related things. So that's my area of research, but also for the youth, I guess the primary school age kids. So I was just wondering, you mentioned gamification, and with the prospect of creating an app, how do you think you can integrate more gamification, such as reward systems and things like that for the youth? For example, if they accrue a certain number of points, they might get one tag on that's free, and that can be linked to their smart rider by the app. So kids really like that.
No, yeah. So yeah, what is the gamification that I can achieve throughout and what more I can do? That was a question. It will really depend on what is the user, what is the information they're trying to deliver. Currently, this project is able to deliver the information that Transport wants us to do. But if there is a deeper aspect, if there is a tag-on system, as you mentioned before, if they want to incorporate and engage that, then there might be some more gamification, as you said, using token system, using repeated there's a lot of things you can do, which you can build into and have that extra aspect added onto it. But currently this delivers information and that we require to do.
Because currently, I'm not sure if you're aware, but because I'm a teacher as well, and a lot of school students avoid pain when they get on the bus.
Okay.
So I'm not sure because sometimes I'd get on the bus and I'd see so many students not paying, and I'm thinking, what's happening? So what we can do is develop like an IOU system where and the kids will be more accustomed to do that, and that can be registered on the Smart Rider as an IOU, and then it can be affiliated with their profile on the app, so then the parents can help and top that up, because every day there are just tons of kids that don't pay for various reasons. So that could be one way of...
Yeah, that is something we can look into.
Well.
No, definitely.
Better than our inspectors jumping on board and yelling at them.
Yeah, we can have an inspector coming in.
Any other questions from the audience? Over in the back, Peter?
So it's partly a comment that a different target audience might be people going to special events like football, who don't normally travel by public transport, particularly the train.
Yeah.
I travel by train all the time. It would be nice to do something that encourages them how to use the transport efficiently.
Yeah.
Because they clog it up, it's busy, but they don't travel normally, so they don't know how to get on efficiently. They're going to games and things, so maybe there'd be good target audience or something like this.
Yeah, definitely.
Do a Docker's version.
Just change the logos. But yeah, that was something we were looking into, filming the train sequence and putting that into the project, but we were running out of time. And I wanted to make this version as best as I could. You'll be able to see in the demonstration area, I wanted to make sure it has nice animation, it is transitioning nicely, as I wanted to make something that I will use as someone who is a 22-year-old. So I want to make sure that it is polished and more people can use it. And then we can model this to more experiences later on. Hey.
Is there any different language
So the content delivery right now is spoken, and that is English. I agree with you there. There is no subtitles right now. We can look into having a different language subtitles. That is something we can look into and have that. Yeah. There is only English right now, but yeah, to answer your question.
Good idea. Any other questions or suggestions?
Or comments?
Oh, no, you're just waving. I'm just waving. Oh, we've got another renter crowd coming in. All right, well, thank you very much, Darp. And Darp's demonstration will be at the front here. We've also got a touchscreen version that you can experiment with as well, as showing on the tile display here. So thank you, Darp. Our very last presentation of the day, last but not least, is Ahmad Allahham. Sorry? Allahham, sorry. Get it right. Ahmad's supervisor is Katerina. And should I say the last name as well? Milkovic, I think it is. Is that right? Close? Not really? Oh, okay. Well, maybe that's good then. Katerina's from the School of Earth and Planetary Sciences, and Ahmad's presentation is on scientific visualisation of asteroid strikes and cratered worlds, which is also a virtual environment presentation, which we eventually shown on the cylinder here. So over to you, Ahmad.
I was planning to open up the presentation with my parents are not here. I'm going to wait for them to come, but they've arrived majestically, so we're going to go straight into the presentation. Hello everyone, my name is Ahmad Allahham. I am a student.
You need to speak up a bit.
Okay, sorry. Graphics. I am a student here at Curtin University. I am an undergraduate student at Curtin University. Effects. I study computer science as my major, which means I can read and write gibberish, also known as programming. I always look into different methods of expanding my skill set and learning more things about computer science and this field. And that's primarily why I decided to join this internship project, which primarily was about Unity, which we will talk about in a bit. There you go. Okay. So my internship project is primarily concerned with visualizing craters. For those of you who don't know, craters are, you can say, holes in planets that are caused by asteroids that hit those planets. And my job was to create a software that's powerful in terms of it being an engine and to display dynamically an immersive experience of the craters. But the problem with that is there's 3 challenges that I was faced with. The first is rendering multiple time steps in a given second. So the data that I have for visualizing these craters is about 260,000 particles in a given frame, and I have to render that plus multiple steps in a given second. So I have to process a lot of things. There's a lot of computational power that's necessary. That's the first hurdle. The second hurdle that I had to overcome is the navigation. Navigation, so when I create the crater, what I have to do is to provide functionality for the user to navigate that crater. So zooming in and out, panning, rotating, and stuff like that, that I had to implement as well. And third, and perhaps most important, is visual immersion. So visual immersion, is that a word? Immersion? Yeah, it is, I think. Okay, visually immersive. So it's very important for the produced simulation to be visually immersive. That's perhaps the core of the software that I have to develop. Because the department, the School of Earth and Planetary Science, already has a software for visualizing craters. However, it's not dynamic enough. It is not very beautiful. It's not very appealing, especially for presentations. And that's where I come in. So for developing this simulation, I had to look for a software. And the team here at the Hive suggested Unity. And Darp gave a great talk about Unity. So I'm not going to go into the details of it. However, I would like to highlight 3 things in Unity. Its ability to do multi-threading, and that's basically, if you've ever done any programming usually you would process lines, 1 line at a time. With multi-threading, you can process multiple lines in parallel. So that's a great ability in Unity. It also has a lot of tools to use. So it has lights, cameras, basically all the things that you would use to set up some sort of, a film or something like that, you can find in Unity, because it's mostly a game engine. However, it's very powerful that you can use it for creating pretty much anything you want. And third, and perhaps most important, is its strong object-oriented backend, which is built on a programming language which is called C#. And this provides great power for modifying the software if you're creating whatever simulation you would like to create. So moving on to the developing of the simulation and overcoming the challenges. So as discussed, the first problem was rendering multiple time steps in a given second. We have so many particles in a given frame, about 260,000 particles in a given frame, and I have to render all of those particles multiple times in a given second. So in 3D as well. So there's a lot of particles. So how am I going to overcome that? Well, I've had a couple of approaches to solve this problem. The first is distribution. Now with distribution, as you can see, with normal distribution of particles, you have the same number of particles in the center as you would have moving away from the center. So you have about 10 particles here, 10 particles in the middle ring, and 10 particles on the outside. But first of all, this introduces holes between the particles, and it's not very efficient use of particles, as you have a lot of particles in the center and very little particles on the outside. So a solution to this is to use distribution that is dependent on its distance from the center. The further you move from the center, the more particles are generated. So at the center, as you can see, there's only a single particle. Move away 4, 6, and then you get more particles as you move out. And this means that there's less holes between the particles and more efficient use of particles, and actually less particles overall. So instead of, say, 260,000 particles in a given plane, you have about 50,000 particles. So you reduce the number of particles by a lot, which is great. So that's the first solution. The second solution, animations. the separation of the loading of the data and the emission of the data. So I have so much data that I have to load, and if you load that before the generation of frames, you can generate frames really, really quickly. So before it was about a second to generate a single frame. Now it's about 1/10 of a second to generate a frame. Simulation. However, if you do that, if you separate the loading of the data from the generation of the data, or the particles, this means that you would have to introduce some form of a loading screen where you would load all the data in the background at first, and then you generate all the particles. So with that, the first problem, which is rendering multiple time steps in a given second, has been solved. Animations. Now to the second problem, which is navigation of the simulation. So my supervisor recommended that I would have at least a single perspective that is capable of zooming in and out of the formed crater, as well as the ability to pan and rotate around the simulation. I discovered that a single perspective might not be enough because there's different things they would like to highlight. If you would like to highlight specific If you would like to highlight specific details, you would probably use a first-person perspective, as you can dive really close into the data and see particular features. But if you would like to get an overall experience of the entire animation, you would use a third-person perspective. So both perspectives are great. You get great things from both perspectives, but each of them has their own advantages. So for the first solution to this problem is to implement a third-person perspective, which allows you to rotate around the generated object. I couldn't find any images of craters, so I just put a planet. But you can figure out, you can just see what's going on. So you get rotation, you get the ability to zoom in and out of the crater. You also get the ability to pan. So panning is just moving up and down. However, in a third-person perspective camera, you get to move around in a plane. So you have a plane and you move around that plane. If you would like to rotate that plane, you would rotate the camera. So that's the first solution. The second solution is to have a first-person perspective, which allows you to look around. This is my preferred perspective because I play a lot of first-person shooters. And it was actually the first perspective that I developed just because it was intuitive. So it allows you to look around, which is great. And it also has the ability to fly. Flying means that you can move in 3D in comparison to the third-person perspective camera, where it was a single plane. Now you can move around in 3D. So if you combine the ability to look around plus the flying, you get a drone-like movement, which is actually very useful for capturing details on the crater that are otherwise difficult to highlight. I actually don't have the built final application on this machine, but I'll show you at the end in the demonstration. But with this, the second problem has been solved. The third and final problem is to create a visually immersive experience. And perhaps it's the most important problem primarily for my supervisor, and for me as well. So the main purpose of creating the software is to be great for presentations, because they already have a software for visualizing scientific data, but they would like to have a very immersive software for the general public. So it's great for presentations. Get up. Yes. Okay, it's great for presentations, and it will get everybody off of their seats. Literally. However, there is a problem with immersion in that, especially in the Unity engine, if you would like to introduce shadows, which provide a great tool for immersion, because you get almost a 3D feel of the entire area, shadows are very expensive in the computer to render, especially when you have 260,000 particles. Each of them has a shadow to render in a dynamic manner. It is very taxing on the computer. And so we have to eliminate shadows, however, have a 3D feel of the software. And the solution to this is to apply a particular surface shader, which is called particle surface shader. Unity. So when you apply a particle surface shader, what it does is it simulates a shadow. So when you have an object and you shine a light onto that object, you get a bright area and a dark area on the back. With a particle surface shader, it picks a certain color. You choose that color, and it colors the surfaces of that object with different colors, different shades of the same color. And this simulates the effect of a shadow even though there isn't a shadow at all. So this is a great workaround of having a shadow and still having the immersive qualities of a shadow. So with this, the third problem has been solved. And now I was hoping to show the simulation. I don't think I don't have it. Okay, I don't have the simulation in the presentation at the moment. But I will show you at the end, as this is the last presentation. You'll get to see on the cylinder. This was actually very hard to line. I was trying to get like a keyboard effect. It was very difficult to line up. I don't know if it's visible, but yeah. So with this, all the problems are solved, and you will see the simulation in a bit. And thank you so much for listening.
Questions from the audience?
Two questions. First, why do you have to make the rest of our slideshows look bad? Second, is it possible that this engine could be used with data sets for things other than meteorite impacts?
Good question. As long as it comes in the format that the program expects it to come, it should be able to work. So the data set, I didn't actually show you the data set itself, but my data set is basically x and y coordinates of particles, as well as their pressure values. So if it comes in that format, it will pretty much display whatever it is. So if it comes in that format, it will display it, hopefully. I didn't test it, but it should work. Yep.
You can answer the first question.
You have to flex. I have to flex at some point.
What did you use to create that?
Yes.
Oh, the presentation? PowerPoint, actually. Nothing fancy. All the effects I used are actually in the PowerPoint, like normal PowerPoint effects. You just have to dig deep and find those effects. But
And no Unity.
Not Unity.
Not Unity
no.
this time.
just PowerPoint.
Where did you get the actual characters and the objects and things like that?
Combination of Google.com and also a feature in PowerPoint called icons, which you can just click the icons, you choose the icon that you want, put it, you can scale it and stuff like that. But there is a particular effect that I use, which is called morph, which is also in PowerPoint, but it's mostly all the animations that you see between the slides. Yeah, so I would have like multiple slides. Yeah. Just the presentation. Yes, I would have a single slide, and then I would duplicate that slide and move things around. And then when you go to the next slide, it actually animates all the different objects that you had in that slide. So it's actually very, very simple. You just have to find it. Yeah.
So drifting back on topic, can you foresee this being rolled out to a head-mount display use or version?
Absolutely, absolutely. According to Michael, it's basically a click of a button to go into VR with a bit of modification in the code.
Does the content suit that kind of presentation? I
would say so, because you do have a first-person perspective,
yep,
which is VR pretty much. So yeah, a bit of tinkering in the code and you get yourself VR. But I don't know how to do it, but it's possible. We got Ben for that.
And how many Unity projects have you developed previously?
Oh, multiple, like 0. Yeah. This is the first. So
this is a bit of a trend, and it just demonstrates what sort of amazing skills these students have got, and also the great resources that are available, both online and also through the HIVE team to get these, deliver these.
I don't have an acknowledgement slide, unfortunately. I forgot. I thank all of you for coming.
Supporting, helping.
Everything. Oh, and family for making it on time as well.
Good question. So you were talking about the shadows and how you have so many particles as possible. So I was just wondering, is there a way you can put a fix a global class on certain particles that are closest to the user?
Right.
Applying the shadow to those rather than...
Yeah, with the shaders. It's possible. It's just that the shadow goes away like the further you move away from the object, and you kind of lose that feel of immersion when you just see like the shadow disappear sort of thing, which is what I had at the moment. So I had a short field of view. So if you move close to the object, you get a shadow, move away from it, it goes away. Improves like the running of the application. It just doesn't look nice. So I thought this was a better solution. Yeah.
Okay, any other questions? If not, I think we'll thank Ahmad for his presentation. And thank you to all the presenters today, Lauren, Isaac, Erin, Andrew, Jack, and in the afternoon, Harrison, Daniel, Benjamin, Darp, Ahmad. And we'll have now a sort of a 10 or 15 minute break. By all means, there's the cafe outside. You can grab yourself a coffee. Just remember, you can't bring it back in here. There's also the exhibition, both the exhibit just out here in the corridor, the large AE1 silhouette on the wall in the atrium, and also the new exhibition in the North and South galleries. So have a look there and come back. And on this one, we'll have Ahmad's project on the wedge in the back with the head-mount display. That'll be Harrison's project. Harrison isn't here, but Stephanie will be here to walk you through that. Over here at the wedge, sorry, over here at the dome, or actually on the 4K display, we'll have Benjamin's project. Hopefully we've managed to get some of Darp's 360-degree videos running on the dome display. And on the tile display here, we'll have Darp's project and who have I forgotten? Daniel's project. All right, so thank you for coming. Hope you've enjoyed it all. Just to remind you that the students have also in the process of finalising their reports, and we'll be making those available as well. If you've got any more interest or specific questions about a project, by all means, come and chat with each of the students. They'll be here this afternoon to show their projects. Put on the head-mounted display, try them out, kick the tyres, and thank you for coming.